Time is the most measured quantity in science, and one of the least understood. We track it to within a fraction of a second across billions of years, build entire technologies around its precision, and organize every experiment we run according to its passage. Yet when physicists ask what time actually is, the agreement breaks down almost immediately. Modern physics has established several things about time that contradict ordinary experience, and it has established them through measurement, not speculation. Time runs slower for objects that move quickly, and this has been confirmed with clocks flown on aircraft and satellites. Time runs slower near heavy masses, which is why the clocks aboard the global positioning system must be corrected every day to stay accurate. There is no single present moment shared across the universe, because two observers moving differently will disagree about which events happen at the same time. And in the deepest equations physicists have written, the ones that attempt to combine gravity with the quantum world, time sometimes disappears from the mathematics entirely. None of these are thought experiments. They are results, drawn from decades of careful observation, and together they describe a universe in which time behaves nothing like the steady, universal flow we assume it to be. This is an investigation into what those results mean. It asks how time can slow, bend, and split, whether the passage we feel is real or a feature of human perception, and whether time might not be fundamental at all. It begins with the simplest and hardest question in the subject. What is time? Ask a physicist to define time, and you are likely to get a pause before an answer. This is not because the question is trivial. It is because time resists the kind of definition we can give to almost anything else. We can define mass by how much a thing resists being pushed. We can define temperature by the average motion of particles. We can define distance by comparison to a fixed standard, a certain number of wavelengths of light emitted by a specific atom. But when we try to define time, we find that almost every definition we reach for already contains the idea of time inside it. We say time is what clocks measure, but a clock is only a device that undergoes regular change, and change already assumes that time is passing. We say time is the progression from past to future, but progression is itself a temporal word. We circle the concept and find that it will not sit still long enough to be pinned down. The oldest recorded struggle with this problem is often traced to the philosopher Augustine, writing more than 16 centuries ago, who confessed that he knew perfectly well what time was until someone asked him to explain it, at which point he found he could not. That admission has aged remarkably well. It captures something that remains true even now, after all the mathematics and all the instruments. Time is intimately familiar and yet strangely opaque. We live inside it so completely that we struggle to step outside it far enough to see what it is. For a long stretch of human history, this puzzle belonged mostly to philosophers, because there was no way to test any answer. That changed when physics began to treat time not as a mystery to be contemplated, but as a quantity to be measured. Once you decide to measure something, you are forced to become precise about what you are measuring, and precision has a way of exposing hidden assumptions. The moment scientists started building better and better clocks, they began to notice that time did not behave the way common sense predicted. But before we reach those discoveries, it is worth being clear about what the ordinary human picture of time actually contains, because nearly every part of it will eventually come under pressure. The everyday view holds several beliefs at once, usually without examining them. The first is that time is universal, that a second here is the same as a second anywhere, and that the whole universe shares a single ticking rhythm. The second is that time flows, that there is a moving present, a now, that advances steadily from the past into the future. The third is that this flow has a fixed rate, always moving forward at the same speed, never faster or slower. The fourth is that time is the same for everyone, that if two people synchronize their watches and go their separate ways, their watches will still agree when they meet again. Each of these beliefs feels not merely true, but necessary, as though the universe could not function any other way. And each of them, under the scrutiny of modern physics, turns out to be either wrong or far more complicated than it appears. Consider the sense that time flows. It is perhaps the most powerful intuition we have, and also the most difficult to locate in the physics. When we say that time flows, we usually mean that the present moment moves, that now keeps advancing, leaving completed events behind it and pulling unrealized events into being. But ask how fast time flows, and the question dissolves. Speed is measured in distance per unit of time, so many meters per second, so many kilometers per hour. To ask how fast time itself moves, we would have to say how many seconds pass per second, which is not a rate at all, but simply the number 1. The flow of time, examined closely, does not have a velocity, because velocity already requires time to define it. This is a strange result. One of our deepest convictions about time turns out to be something we cannot even express without contradiction. Physicists have responded to this in different ways. Some argue that the flow of time is an illusion, a feature of how human consciousness processes the world, rather than a property of the world itself. On this view, the universe simply contains events laid out in a certain order, and the sense that we are moving through them is something the brain generates, much as it generates the sense of a continuous visual field out of discrete signals from the eyes. Others insist that the flow is real, and that any physics which cannot capture it is incomplete, missing something essential about the nature of reality. This disagreement is not settled, and it is not a minor quibble at the edges of the subject. It sits at the very center. Two serious camps of physicists and philosophers look at the same equations and the same experiments and come away with opposite conclusions about whether the passage of time is a fact of nature or a trick of the mind. To see why the question is so hard to resolve, it helps to notice how little the flow of time appears in the actual equations of physics. When we write down the laws that govern how objects move, how forces act, how energy transfers from one form to another, time appears as a variable, a quantity we can assign a value to. But nothing in those equations singles out a particular value as now. The equations describe the entire history of a system, past and future together, as a single mathematical whole. They do not contain a moving marker that says the present is here, and now here, and now here. From the standpoint of the mathematics, all moments are on equal footing, laid out like positions along a line, and the special status we give to the present has no counterpart in the formulas. This is one of the first hints that the way time feels and the way time works may be two very different things. There is another feature of ordinary time worth isolating, because it will return again and again. We treat the past and the future as fundamentally different. The past is fixed, finished, unchangeable. The future is open, uncertain, still to be decided. We remember the past, but not the future. We can affect the future, but not the past. This asymmetry is so basic to experience that it seems almost absurd to question it. And yet, when we look at the fundamental laws of physics, we find that they draw no such distinction. Nearly every basic law works exactly the same, whether time runs forward or backward. If you filmed two billiard balls colliding and played the film in reverse, the reversed collision would obey the same laws of motion as the original. Nothing in the physics of that collision tells you which version is the real one. The laws are, in the technical sense, time-symmetric. They do not prefer forward over backward. This creates a genuine and famous problem. Our experience is saturated with the difference between past and future, yet the underlying rules seem indifferent to it. A cup falls from a table and shatters on the floor, and we never see the reverse. Never see shards gather themselves into a whole cup that leaps back onto the table. But the laws governing every atom in that cup would permit the reverse just as readily as the original. So where does the difference come from? Why does the world we live in have such a strong arrow, such a clear direction, when the laws beneath it do not? This is a question we will return to in depth, because its answer, as far as we have one, reaches into some of the deepest ideas in all of physics, connecting the flow of time to the large-scale condition of the universe itself. For now, the important point is that the ordinary picture of time is not a single simple idea. It is a bundle of separate assumptions: universality, flow, fixed rate, shared duration, the difference between past and future, all tangled together and all taken for granted. Physics has learned to pull these threads apart and test them one at a time, and when it does, the bundle comes undone. Some of the assumptions survive in modified form, others fail outright, and a few turn out to be so deeply confused that it is not even clear what it would mean for them to be true. This is what makes time such a productive puzzle for science. It is not a question that can be answered by discovering one new fact. It is a question that forces us to examine the relationship between what we perceive and what is real, between the mind that experiences time and the universe that seems to contain it. Every time we build a better clock, every time we send a precise instrument into a new regime of speed or gravity, we get another piece of the answer, and the piece rarely matches what we expected. The story of time in modern physics is, in large part, the story of instruments outrunning intuition, of measurements revealing a world that our senses were never equipped to notice. And that is precisely where the investigation has to turn next. If time is so difficult to define directly, then perhaps the way forward is not to define it at all, but to measure it as carefully and as precisely as possible, and to see what the measurements reveal. Because it was in the act of measuring time, more and more finely, that physics first discovered just how far the truth lies from the floor we thought we were standing on. What happens then when we try to measure something that has no shape, no substance, and no location, yet appears to govern everything? The strange thing about measuring time is that we never measure time itself. We only ever measure change. A pendulum swings from one side to the other. A quartz crystal flexes back and forth when a current runs through it. An atom absorbs energy and vibrates at a fixed frequency. In every case, what we are actually watching is a physical system repeating some motion, and we count the repetitions. We call the count time. But the thing we call time, the invisible quantity that supposedly makes the pendulum swing and the crystal flex, never shows itself directly. It leaves no mark, casts no shadow, occupies no place. We infer it entirely from the regular behavior of matter. This is a peculiar situation for a science built on measurement. Nearly everything else physics studies can, in some sense, be pointed at. A mass sits on a scale. A charge deflects a needle. A beam of light lands on a detector and registers its arrival. But time has no location to point to. It is not here or there. It seems to be everywhere at once, or nowhere in particular, depending on how you think about it. And so the entire enterprise of measuring time rests on a quiet assumption, one so natural we rarely notice we are making it. We assume that somewhere in the world, There exists a process that repeats perfectly evenly, tick after identical tick, and that by counting those ticks, we are counting equal intervals of true time. The trouble is that we can never fully verify this assumption from the inside. To check whether a clock is ticking evenly, we would need to compare it against time itself, against some perfect standard of even flow. But we have no access to time itself. All we have are other clocks. So when we ask whether a given clock is accurate, what we are really asking is whether it agrees with other clocks we trust. We check pendulums against quartz, quartz against atoms, one atomic clock against another. The whole system is a network of physical processes agreeing with one another, and we take that agreement as evidence that they are all tracking something real. It works remarkably well. But at no point does anyone hold up time itself and measure a clock against it, because there is nothing to hold up. This is the first deep oddity in the measurement of time. The standard we are chasing is one we can never directly see. For most of history, the clocks available were crude enough that this philosophical worry stayed hidden. Early timekeeping relied on the largest and most reliable repeating process anyone could find: the motion of the sky. The sun rose and set. The stars wheeled overhead and returned to their positions. The moon cycled through its phases. These motions gave the first units of time: the day, the month, the year, and for thousands of years, they were the ultimate reference. Time was defined by the heavens because the heavens seemed to be the steadiest thing in existence. A day was one turn of the sky, and nothing seemed more dependable than that. But as clocks improved, a subtle problem emerged. The heavens, it turned out, were not perfectly steady after all. The length of the solar day varies slightly across the year because the Earth's orbit is not a perfect circle and its axis is tilted. The Earth's rotation itself is gradually slowing, braked by the tides raised by the moon, so that the day is imperceptibly longer now than it was in the distant past. Even the seemingly fixed length of the year drifts when examined finely enough. The very motions that had served as the definition of time were revealed to be irregular, once instruments became precise enough to catch the irregularity. This was an important lesson, and it would repeat itself throughout the history of timekeeping. Every time we found a process we trusted to define time, a better instrument eventually showed that the process wandered. The reference always turned out to be less perfect than the tool measuring it. This drove a long migration towards smaller and smaller repeating systems, on the reasoning that smaller processes might be more stable and less exposed to the disturbances that affected large bodies. Mechanical clocks with pendulums improved on the sky, though they were sensitive to temperature, to changes in gravity from one location to another, even to the tiny disturbances of a passing truck. Quartz clocks improved on pendulums, using the steady vibration of a crystal, and they were good enough to reveal fluctuations in the Earth's rotation that no one had been able to detect before. But the true revolution came when timekeeping moved down to the scale of the atom, because atoms offered something that no larger system could. They were, as far as anyone could tell, perfectly identical to one another, and their behavior was governed by unchanging physical constants rather than by the particular history of any one object. An atom of a given element responds to energy in a fixed and characteristic way. When it absorbs or emits radiation of exactly the right frequency, it does so at a rate determined by the fundamental structure of the atom, a rate that should be the same for every atom of that element, everywhere in the universe, at every moment in cosmic history. This is a profound property. A pendulum in one city differs slightly from a pendulum in another. A quartz crystal ages and changes over the years. But an atom of a particular element in one laboratory is, to the best of our knowledge, exactly the same as an atom of that element on the other side of the galaxy. If you want a repeating process that does not depend on where you are or what has happened to your equipment, an atomic transition is close to the ideal. This is why the modern definition of the second is no longer tied to the sky at all. The second is now defined by counting a specific, enormous number of oscillations associated with a particular transition in a certain kind of atom. When that count is complete, 1 second has passed, by definition. The heavens have been retired as the keeper of time, replaced by a process happening inside atoms, a process so regular that the best atomic clocks would drift by less than a second over spans of time longer than the current age of the universe. We have, in a sense, found the steadiest tick nature seems willing to offer, and we have made it the foundation of all our timekeeping. And yet even this triumph does not escape the original puzzle. An atomic clock is still just a physical system that repeats. It is more stable, more universal, more independent of local disturbance than anything that came before. But it is still change being counted, not time being seen. We trust it because it agrees, to extraordinary precision, with other atomic clocks built on the same principle. We trust it because the physics that governs it is the same physics that governs everything else, and that physics has passed every test we have devised. But the deepest assumption remains untouched. We are still counting the ticks of a physical process and calling the count time, still inferring an invisible quantity from the visible behavior of matter. We have made the inference vastly more precise. We have not made it any less of an inference. There is a further subtlety that becomes visible only at these levels of precision, and it points ahead to some of the most important discoveries in the physics of time. Once clocks became accurate enough, they revealed that two identical clocks, built to the same specification and set to the same time, do not always stay in agreement. Move one of them, and it drifts from the other. Raise one of them to a greater height, and it drifts again. These are not flaws in the clocks. They are real effects, and they are reproducible. Identical atomic clocks, functioning perfectly, will disagree if one is carried on a fast journey and returned, or if one spends time higher up than the other. The disagreement is tiny, but it is measurable, and it is exactly what the deeper theories of physics predict. This is the point at which the measurement of time stops being merely a technical challenge and becomes a window into the structure of reality. As long as clocks were crude, it was possible to believe that any disagreement between them was a matter of imperfect craftsmanship, that a truly perfect clock would keep truly perfect time, the same for everyone everywhere. But the atomic clock removed that excuse. Here were clocks as close to perfect as physics allows, and they still disagreed in a lawful and predictable way, depending on how they moved and where they sat. The disagreement could not be blamed on the instruments. It had to be a property of time itself, and this changes the entire character of the investigation. If perfect clocks agree only when they share the same motion and the same location, then the idea of a single universal time, a master clock ticking for the whole cosmos, cannot be right. There is no such master clock. There is only a collection of physical processes, each keeping its own time, and those times do not always match. The rate at which a clock ticks turns out to depend on the clock's circumstances, on how fast it moves and how deep it sits in a gravitational field. Time, measured carefully enough, is revealed to be local rather than universal, personal rather than shared. That revelation raises an immediate and unsettling question. If your clock and mine can disagree simply because we move differently or stand at different heights, then whose time is correct? When we say that a second has passed, Whose second do we mean? And if there is no single answer, if each clock genuinely keeps its own valid time with no master clock to overrule any of them, then what happens to the idea that we all share the same present moment, the same now, ticking forward together across the universe? The idea that everyone shares the same present feels beyond question. Right now, as you follow these words, it seems obvious that everything else in the universe also exists right now, in its own version of this same instant. A friend across the city is doing something at this moment. A star on the far side of the galaxy is burning at this moment. The moon hangs in its orbit at this moment. We picture the entire cosmos as a single vast scene, every part of it sharing one universal present that advances together, tick by tick, into the future. This picture is so natural that it hardly seems like a picture at all. It seems like a description of the way things simply are. Physics says it is wrong. Not incomplete, not approximate, but wrong in a way that cannot be repaired by more careful measurement. There is no universal present. The set of events happening now is not the same for everyone. Two people can look at the very same collection of distant events and genuinely disagree about which of them are happening at this moment, and neither of them is mistaken. This is one of the most firmly established results in all of physics, and it is also one of the hardest to absorb, because it contradicts something we never even thought to doubt. To understand how this can be, we have to start with a fact about light. Light travels at a finite speed. It is a very high speed, fast enough that in everyday life it seems instantaneous, but it is finite, and this finiteness has consequences that reach much further than they first appear. Because light takes time to travel, we never see distant things as they are now. We see them as they were when the light left them. Look at the sun, and you see it as it was several minutes ago, because that is how long its light takes to reach us. Look at a distant star, and you may be seeing light that left it centuries ago, so that you are looking not at the star's present, but at its distant past. The night sky is not a snapshot of the universe now. It is a layered image of many different pasts, each object shown at a different moment, depending on how far its light had to travel. At first, this seems like nothing more than a delay, a kind of cosmic postal lag. You might think that the distant star still has a real present, a true now of its own, and that we simply have to wait for the news to arrive. But the deeper discovery of modern physics is that this assumption falls apart when we ask a more careful question. The finiteness of light's speed is not just a limit on information. It is bound up with the structure of time itself, because that speed turns out to be an absolute feature of the universe, the same for every observer, no matter how they move. This is the strange fact at the heart of the matter. Ordinarily, speeds add up in a simple way. If you walk forward along a moving train, your speed relative to the ground is your walking speed plus the train's speed. If you throw a ball forward from a moving car, the ball moves faster relative to the road than it would if you threw it while standing still. Every speed we deal with in daily life behaves this way, but light does not. Measure the speed of a beam of light while standing still, and you get a certain value. Measure it again while racing toward the source of that light as fast as you can, and you get exactly the same value. Chase the light, and it does not close the gap any faster. Flee from it, and it does not fall behind. The speed of light is the same for everyone, regardless of their own motion. This has been tested with extraordinary precision, and it holds without exception. Take a moment to feel how odd this is. If you run toward an oncoming beam, common sense insists that the beam should approach you faster, its speed and yours combining. But it does not. It approaches at the same fixed speed as always. The only way this can be true, the only way everyone can measure light at the same speed, no matter how they move, is if something gives way. And what gives way, it turns out, is time itself, along with space. In order to keep the speed of light constant for everyone, the universe adjusts the rates at which clocks tick and the lengths across which distances are measured. Time and space bend to preserve the constancy of light. This was the revolutionary insight, and its consequences unravel the idea of a shared present completely. Here is how the shared present comes undone. Deciding that two distant events happen at the same time, that they are simultaneous, requires a way of comparing clocks separated by space. But since light takes time to travel, and since its speed is the same for everyone regardless of motion, the comparison depends on how the observer is moving. Consider two events, one far to your left and one far to your right, and suppose that from your point of view, standing still, the light from both reaches you at the same instant, so you conclude they happened simultaneously. Now consider someone moving past you, traveling from left to right. Because of their motion, the geometry of the situation changes for them. The light from the two events reaches them in a way that, when they account for their own movement and the fixed speed of light, leads them to conclude that the two events did not happen at the same time at all. From their perspective, one clearly happened before the other, and there is no experiment that can settle who is right, because there is nothing to settle. Both descriptions are equally valid. Simultaneity, the sameness of two moments across a distance, is not a fixed fact about the universe. It depends on the observer. This is called the relativity of simultaneity, and it is the precise sense in which the universal present collapses. Two observers moving differently will slice up the events of the universe into different sets of now. What one calls the present, another calls the past, and a third calls the future, and each is entirely correct within their own frame. There is no privileged slicing, no true division of the universe into what has happened and what is yet to happen, that every observer must accept. Each state of motion carries its own definition of the present, and the universe honors all of them equally. The consequences of this run deep. If your now and my now can differ simply because we move differently, then the present is not a universal feature of reality. It is not a moving wave sweeping through the cosmos, the same everywhere. It is more like a personal orientation, a particular way of dividing events that belongs to a particular observer in a particular state of motion. Change your motion, even slightly, and you shift your own definition of what is happening now on the far side of the universe. The effect is tiny for the small speeds of everyday life, far too small to notice, which is why our intuition never developed any sense of it. But it is real, and at large distances, even modest changes in motion can shift the calculated present by surprisingly large amounts, so that walking across a room could correspond, for events billions of light years away, to a shift of years in what you would calculate as happening now. This leads to a startling way of thinking about the whole of time. If different observers slice the universe into different sets of now, and if all these slicings are equally valid, then it becomes difficult to maintain that only the present is real while the past has vanished and the future does not yet exist. What one observer regards as the still unrealized future, another, moving differently, may already regard as the settled past. For both descriptions to be valid, as the physics insists they are, the events in question must in some sense be equally real for both observers. The future event that one person has not yet reached is an event that another person, in a different state of motion, already counts as having happened. And an event that has genuinely happened cannot be unreal. Follow this reasoning to its conclusion, and you arrive at a picture in which past, present, and future all exist on the same footing, laid out together, with no objective moving present to single out one slice as the only real one. On this view, the sense that the present is special, that now is the one true moment while the past is gone and the future is open, becomes a feature of individual perspective rather than a fact about the universe. The universe, taken as a whole, would contain all events at once, and the flow we feel, the sense of the present marching forward, would be something added by the observer rather than something present in the events themselves. Not every physicist accepts this conclusion, and we will come to the disagreement because it is one of the genuine open questions rather than a settled result. But the step that leads to it, the collapse of the universal present, is not in dispute. The relativity of simultaneity has been confirmed in countless experiments, woven into the design of technologies we use every day, and never once contradicted. Whatever we ultimately decide about the reality of the flow of time, we can no longer believe in a single cosmic now shared by all. That much is gone. Which forces the next question, and it is a physical one rather than a philosophical one. We have seen that observers disagree about simultaneity because of how they move. But the deeper theory does not merely rearrange which events count as simultaneous. It predicts that motion changes the very rate at which time passes, that a clock in motion ticks slower than a clock at rest, and that this slowing is not an illusion of perspective, but a measurable physical fact. If that is true, then two travelers who move differently will not only disagree about the present, they will age at genuinely different rates, and when they meet again, one will be younger than the other. How can motion itself reach into a clock and slow the passage of time? The claim sounds like something from fiction. Move fast enough, and time slows down for you. Travel at a great speed and return, and you will have aged less than those who stayed behind. It has the flavor of a tall tale, the kind of thing that ought to collapse the moment anyone checks it carefully. But it has been checked many times with instruments of great precision, and it holds every time. Motion slows time. The effect is real, it is measurable, and it is now so well established that engineers must account for it in the design of ordinary technology. The task is to understand how something as simple as movement can reach into a clock and change the rate at which it ticks. Begin with where this prediction comes from, because it is not an arbitrary guess. It follows directly, unavoidably, from the fact we have already met, that the speed of light is the same for every observer no matter how they move. Once you accept that fact, and the experiments leave no room to reject it, the slowing of moving clocks follows as a matter of logic. To see why, imagine the simplest possible clock, one built from light itself. Picture two mirrors facing each other with a single pulse of light bouncing straight up and down between them. Each round trip, each bounce up and back, counts as one tick. This is a perfectly good clock. The light travels a fixed distance between the mirrors, at the fixed speed of light, and so each tick takes a fixed amount of time. Nothing could be simpler. Now set this clock in motion. Imagine it mounted sideways on a fast-moving vehicle, gliding past you while the light continues bouncing between its mirrors. From the point of view of someone riding along with the clock, nothing has changed. The light still goes straight up and down, mirror to mirror, each tick the same as before. But from your point of view, standing still and watching the clock rush past, the light does something different. Because the whole apparatus is moving sideways while the light travels between the mirrors, the light no longer goes straight up and down as you see it. By the time the pulse reaches the top mirror, that mirror has moved sideways, and by the time it returns, the bottom mirror has moved too. So from your vantage, the light traces out a longer, slanted path, a zigzag rather than a straight line, because it must cover sideways distance as well as up and down distance to keep up with the moving clock. Here is where the constancy of light forces the crucial conclusion. The light in the moving clock has to travel a longer, slanted path as you see it. But light always moves at the same fixed speed. It cannot go faster to make up for the longer path. And if it covers a longer distance at the same speed, it must take more time to complete each bounce. More time per tick means the moving clock ticks slower, from your point of view, than it does from the point of view of someone riding along with it. The moving clock runs slow, not because anything is wrong with it, but because the geometry of its light path, combined with the unchanging speed of light, leaves no other possibility. This is the origin of what is called time dilation, the slowing of time with motion, and you can see that it is not an added assumption, but a direct consequence of the one fact we started with. The effect is completely symmetric, which is one of the features that makes it so difficult to hold in the mind. To you, the moving clock runs slow. But to someone moving along with that clock, it is your clock that runs slow, because from their point of view, they are the ones at rest, and you are the one moving past them. Each observer sees the other's clock ticking more slowly. This is not a contradiction, though it sounds like one. It is a consequence of the fact that motion is relative, that there is no absolute state of rest against which all motion is measured. Each observer is entitled to consider themselves at rest and the other in motion, and within each perspective, the moving clock genuinely runs slow. The symmetry only breaks when the observers are brought back together to compare, which requires one of them to change their motion, to turn around and return. And it is that change, that departure from steady motion, that resolves the situation and determines who has aged less. For a long time, this remained hard to test because the effect is minuscule at ordinary speeds. The slowing depends on speed in a very particular way. At the speeds of daily life, even the speeds of fast aircraft, the slowing is so slight that it barely registers, a matter of tiny fractions of a second. Only as speeds climb toward a significant fraction of the speed of light does the effect grow large. This is why we never notice it. Nothing in our ordinary experience moves fast enough for the slowing of time to become apparent. Our intuitions about time were formed entirely in the realm of slow motion, where the effect is hidden, which is exactly why the effect feels so alien when we finally encounter it. But nature provides its own fast-moving clocks, and they confirm the prediction directly. High in the atmosphere, incoming radiation from space strikes the upper air and produces a shower of tiny particles, some of which are inherently unstable, existing only for a fleeting span before they decay into other particles. These particles have a well-known lifetime, measured precisely in the laboratory, and that lifetime is extremely short. It is so short that even moving at nearly the speed of light, these particles should decay long before reaching the ground. By any straightforward reckoning, almost none of them should survive the trip down through the atmosphere, and yet they arrive at the surface in large numbers, far more than should be possible if their internal clocks ran at the normal rate. The reason is time dilation. Because they move so close to the speed of light, their internal clocks, the processes that count down to their decay, run slow from our point of view. Their brief lifetimes are stretched, extended just enough for many of them to complete the journey. They serve as natural, fast-moving clocks, and they read exactly what the theory predicts. The slowing of time is not a paradox to be argued about. It is written in the rain of particles falling through the sky at every moment. The same effect has been confirmed with actual clocks, deliberately moved and compared. Precise atomic clocks have been flown around the world on aircraft and compared afterward with identical clocks left on the ground. The flown clocks, having moved at high speed, return showing slightly less elapsed time than the stationary ones, by exactly the small amount predicted. The difference is tiny, measured in fractions of a millionth of a second, but the clocks are precise enough to catch it, and the result matches the theory. Two clocks, identical in every way, set to the same time, disagree after one has traveled and returned. The traveler's clock has ticked fewer times. Less time has passed for the clock that moved. This is worth pausing on, because it is easy to slide past its real meaning. The slowing is not an illusion, not a matter of the clock appearing to run slow while secretly keeping true time. The moving clock genuinely experiences less time. Every process that depends on time slows together with it in perfect step. If the traveler carried a mechanical watch, a beating heart, a growing plant, a decaying particle, all of them would slow by exactly the same factor, because all of them are governed by the same underlying time. There is no way to tell from the inside that time is running slow, because everything slows together, including the very processes you would use to check. From within the moving frame, a second feels like a second, a heartbeat like a heartbeat. It is only when the traveler returns and compares with those who stayed behind that the difference reveals itself. In fewer heartbeats, fewer ticks, a body that has aged less. Push this to its extreme, and it produces one of the most famous scenarios in all of physics, in which a traveler journeys outward at close to the speed of light and returns, to find that far more time has passed for everyone who remained than for the traveler. If the speed were high enough and the journey long enough, the traveler might return after what felt to them like a few years, to find that decades or centuries had elapsed at home. This is not a loophole or a trick of interpretation. It is a straightforward consequence of the slowing of time with motion, applied at high speed. The traveler's clock, along with the traveler's body and mind and everything else, simply ran slow relative to those left behind, and so accumulated less time over the course of the trip. When the two are reunited and their clocks compared, the traveler's clock has counted fewer seconds, and the traveler is genuinely younger. Nothing has been faked. Time itself passed differently for the two of them. What makes all of this more than a curiosity is that it is already built into technology we depend on. The satellites that provide global positioning carry precise clocks, and those satellites move at high speed relative to the ground. Because of their motion, their clocks run slow compared to clocks on the surface, by a small but significant amount. If this slowing were not corrected, the positioning system would quickly drift into serious error, its location estimates degrading badly within a single day. The engineers who built the system had to account for the slowing of time with motion in order to make it work. Every time such a system guides a traveler to a destination, it is silently relying on the fact that moving clocks run slow, a fact confirmed continuously, second by second, in orbit above our heads. So motion reaches into a clock and slows time, and it does so because of the unbending constancy of the speed of light. This much is established beyond serious doubt. But motion is not the only thing that changes the rate of time. The satellites overhead reveal a second effect, one that pulls in the opposite direction and is even stranger in its origin. For those same orbiting clocks do not only move fast, they also sit far above the Earth, higher up in the planet's gravity than any clock on the ground. And it turns out that height in a gravitational field changes the rate of time as well, so that a clock lifted away from a heavy mass ticks faster than one held close to it. If motion can slow time, How can gravity, the pull of sheer mass, reach in and change its rate as well? The satellites overhead carry two effects at once, pulling in opposite directions. Their motion slows their clocks, as we have seen. But their height speeds those same clocks up, and the second effect is even more surprising than the first, because it has nothing to do with speed at all. A clock does not have to be moving to run at a different rate. It only has to sit at a different height in a gravitational field. Lift a clock away from a heavy mass, and it ticks faster. Lower it toward that mass, and it ticks slower. Gravity, the plain pull that holds us to the ground, reaches into every clock and changes the rate at which time flows. To understand how, we have to look at gravity in a completely different way than the familiar one. We usually think of gravity as a force, an invisible pull reaching out from heavy objects to draw other objects toward them. The Earth pulls the moon, the sun pulls the Earth, and everything with mass tugs on everything else. This picture works well for many purposes, and it is how gravity was understood for centuries. But it turns out to be a surface description of something deeper. The more fundamental account does not treat gravity as a force acting across space at all. It treats gravity as a feature of the geometry of space and time, a bending or curving of the very stage on which events unfold. Mass does not reach out and pull. Instead, mass warps the space and time around it, and other objects, moving through that warped setting, follow paths that appear to us as the effects of gravity. This idea is difficult, so it is worth building up carefully. Start with a thought that connects gravity to something we have already seen. Imagine you are sealed inside a windowless chamber, unable to see out, and you feel yourself pressed to the floor with a steady weight, exactly as you would feel standing on the ground. From inside, you cannot tell what is producing that sensation. It could be that your chamber is sitting at rest on the surface of a planet, held down by that planet's gravity. Or it could be that your chamber is far out in empty space, away from any planet, being steadily accelerated forward, so that the floor is pushing up against you the way the floor of an accelerating vehicle presses against your back. From inside the sealed chamber, these two situations feel identical. There is no experiment you could perform, no measurement you could make, that would distinguish the pull of gravity from the push of steady acceleration. They are, as far as physics inside the chamber is concerned, the same thing. This equivalence, the indistinguishability of gravity and acceleration, is a cornerstone of the deeper theory of gravity, and it leads directly to the effect of gravity on time. We already know that motion affects time. If gravity and acceleration are fundamentally the same, then gravity must affect time as well. Follow the reasoning through the sealed chamber. Suppose the chamber is accelerating forward through space, and a pulse of light is sent from the floor toward the ceiling. During the brief moment the light takes to travel upward, the chamber speeds up because it is accelerating. The ceiling, rushing forward to meet a slower path, receives the light in a slightly altered state compared to how it was emitted. When the calculation is worked through, the light arriving at the ceiling is found to be shifted, its rhythm stretched, as though the source that emitted it were running slow. A clock at the floor, seen from the ceiling, appears to tick more slowly than a clock at the ceiling. Now apply the equivalence. If this happens in an accelerating chamber, it must also happen in a chamber sitting still in gravity, because the two cannot be told apart. So in a gravitational field, a clock lower down, deeper in the field, closer to the mass, runs slower than a clock higher up. The floor is like the position deeper in gravity, the ceiling like the position higher up. Time runs slower the deeper you are in a gravitational field, and faster the higher you climb out of it. This is gravitational time dilation, and it is entirely distinct from the slowing caused by motion. It depends not on how fast you move, but on where you sit in the warping of space-time produced by nearby mass. The effect is small near a modestly sized planet, but it is not too small to measure, and it has been confirmed directly and repeatedly. In one of the classic demonstrations, physicists compared the rhythm of radiation emitted at the bottom of a tall tower with the same radiation received at the top, a height difference of only a few tens of meters. Even across that modest span, the difference in gravitational height produced a measurable shift in the rhythm, exactly as predicted. Time ran slightly slower at the bottom of the tower than at the top, by a tiny but detectable amount. More recently, atomic clocks have become precise enough to register the difference in the rate of time between two positions separated by height differences smaller than a single meter. Raise an atomic clock by the height of a step, and it ticks measurably faster than the one below it. The effect is not confined to extreme environments. It is present everywhere, at every change in height, all the time. Your head ages very slightly faster than your feet because it sits a little higher in the Earth's gravity. The difference over a lifetime is unimaginably small, far too small to notice, but it is real, and clocks precise enough to detect it now exist. This brings us back to the satellites, where the two effects meet and can be weighed against each other. A positioning satellite moves quickly, and its speed slows its clock relative to the ground. But it also orbits high above the Earth, far out in weaker gravity, and this height speeds its clock up relative to the ground. The two effects oppose each other. At the altitude of these satellites, the speeding from height outweighs the slowing from motion, and the net result is that the satellite's clock runs faster than an identical clock on the surface, by a definite and predictable amount each day. The engineers who built the system had to calculate both effects, the slowing from motion and the speeding from reduced gravity, combine them, and correct for the total. If they had left out the gravitational effect, the system would fail just as surely as if they had left out the effect of motion. Both are essential. Both are confirmed continuously by the system's successful operation. Every accurate position fix is a running confirmation that gravity changes the rate of time. The picture that emerges from all this is a strange and beautiful one. Mass warps the space and time around it. Near a heavy object, time runs slow, and the closer you get, the slower it runs. Far from any mass, out in the emptiness between the stars, time runs faster. The Earth, the Sun, every massive body, sits at the bottom of a well of slowed time, a region where clocks tick more sluggishly than they do farther out. We live our whole lives near the bottom of the Earth's well, our clocks running slightly slow compared to the universe at large, and we never notice because everything around us shares the same slowing. It is only by lifting a clock, or by comparing with a clock far away, that the difference reveals itself. Consider what this means for the earlier idea of a single universal time. We had already seen that motion breaks it, that moving observers disagree about the rate of time and about which events are simultaneous. Now gravity breaks it further. Even observers who are not moving relative to one another will disagree about the rate of time if they sit at different depths in a gravitational field. A clock in the basement and a clock in the attic, both perfectly still, both perfectly accurate, will drift apart. The basement clock forever falling behind. There is no height at which the true rate of time is found, no privileged position whose clock keeps the real time while others run fast or slow. Every position keeps its own valid time, and those times differ according to the local warping of space-time. The dream of a master clock, ticking the same for the whole universe, is not merely bent by gravity, it is abolished. And the effect grows without limit as the mass grows more concentrated. Near an ordinary planet, the slowing of time is slight. Near a more massive and compact object, it becomes pronounced. And near the most extreme objects the universe contains, where an enormous mass is packed into a tiny region, the slowing of time becomes extreme beyond anything in our experience. As you approach such an object, time runs slower and slower relative to the outside universe, until, at a certain boundary, it appears from the outside to slow to a complete stop. A clock lowered toward that boundary would seem, to a distant observer, to tick ever more sluggishly, its final approach stretching out toward forever, never quite arriving. Something happens to time at the edge of these objects that pushes the theory to its limit and beyond. If gravity slows time, and if gravity can grow without bound, then what becomes of time at the edge of a region where gravity has grown so strong that not even light can escape? Around the most extreme objects the universe contains, gravity grows so strong that the slowing of time reaches a limit our ordinary language was never built to describe. These objects form when a great mass collapses into a region so small that the warping of space-time around it becomes overwhelming. At a certain distance from the center, the warping reaches a threshold beyond which nothing can escape, not even light. This threshold is not a solid surface. It is a boundary in space-time, a point of no return, marking the edge of a region from which no signal, no object, no influence of any kind can ever climb back out. We call this boundary the horizon, and what happens to time near it stretches the theory of gravity to its breaking point. Recall what we have established. Time runs slower the deeper you sit in a gravitational field, and the effect grows as the field grows stronger. Near an ordinary planet, the slowing is slight. Near a compact, massive object, it becomes severe. And as you approach the horizon of one of these collapsed objects, the slowing grows without limit. From the point of view of a distant observer watching something fall toward the horizon, time for the falling object appears to slow more and more as it nears the edge. If you watched a clock descending toward the horizon, you would see it tick ever more slowly, its rhythm stretching out, the intervals between ticks growing longer and longer. As the clock approached the horizon, it would appear to nearly freeze, its final approach seeming to take longer and longer, the last stretch drawing out toward an eternity. From the outside, the clock never quite reaches the horizon. It seems to hover just short of it, frozen in an approach that never completes, its light growing dimmer and more stretched until it fades from view entirely. This is one of the most striking predictions in the physics of gravity, and it reveals something crucial about the nature of time near these objects. What the distant observer sees is not an illusion in the sense of a mistake. It is a genuine feature of how time is structured in that warped region. But here is the strange part. The observer falling toward the horizon experiences nothing of the sort. For the one who falls, time continues to pass normally, second following second, with no sense of slowing at all. From the falling observer's point of view, the horizon is not a wall where time freezes. It is a boundary that can be crossed, and crossed in a finite, ordinary amount of their own time. They fall toward it, reach it, and pass through it, all while their own clock ticks steadily onward. There is no moment from the inside at which time grinds to a halt. So we have two accounts of the same event, and they could hardly be more different. From outside, the falling clock takes forever to reach the horizon and never actually crosses it. From inside, the falling clock crosses the horizon in a finite time and continues on. Both accounts are correct. This is not a case where one observer is right and the other is mistaken. It is a case where time itself is so severely warped that two observers, related by the geometry of the situation, genuinely cannot agree on whether an event ever happens. For one, the crossing lies eternally in the future, always approaching, never arriving. For the other, the crossing is a completed fact, already behind them. The disagreement is not about perception. It is about the structure of time in a region where gravity has bent space-time beyond anything our intuitions can follow. To make sense of how both can be true, it helps to think about what the horizon actually is in terms of the geometry of space-time. We are used to thinking of directions in space as the ones we can move freely through, and the direction in time as the one we are carried along, always into the future, unable to reverse. Near one of these collapsed objects, the warping becomes so extreme that this familiar arrangement changes. Inside the horizon, the direction that points toward the center takes on the character that time has for us on the outside. Moving toward the center becomes not a choice among directions, but an inevitability, as unavoidable as our own passage into the future. Just as we cannot avoid moving forward in time, an object inside the horizon cannot avoid moving toward the center. The future itself, inside that boundary, points inward. This is why nothing can escape. Escaping would mean moving in a direction that has become, in effect, the past. And that is as impossible inside the horizon as traveling into yesterday is for us outside it. This reworking of the roles of space and time explains the frozen appearance from outside. The horizon marks a place where the warping of time relative to the distant universe becomes total. Signals climbing out from near the horizon are stretched more and more severely, their rhythm slowed, their light shifted toward longer and longer wavelengths, carrying less and less energy until they fade beyond detection. The infalling object is not destroyed at the horizon from its own point of view, but its connection to the outside universe is progressively severed, its final signals stretched toward an infinite slowness that the outside can never see complete. The freezing is real as a feature of the outside observer's time, and the crossing is real as a feature of the infalling observer's time, and there is no higher vantage from which one of these is the true account and the other false. Each is the honest description within its own frame. The extremity of what happens to time near these objects does not stop at the horizon. It grows more severe within. As the infalling observer continues toward the center, the warping intensifies without limit, and the theory that has served so well up to this point begins to predict its own failure. At the very center, the theory says, the warping of space-time becomes infinite, a place where the curvature grows beyond any bound and the equations that describe gravity stop yielding sensible answers. This is not a triumph of the theory, but a signal of its limit. When a physical theory predicts infinite values, it is usually telling us that it has been pushed beyond the range where it applies, that something is missing, some deeper description that would smooth away the infinity and reveal what is really happening. The center of one of these objects is such a place. Our best theory of gravity points to it, describes the approach to it, and then breaks down at it, unable to say what time and space actually do there. This breakdown matters enormously for the deeper question of what time is, because it marks one of the two great frontiers where our understanding runs out. The theory of gravity that gives us the warping of time, the slowing near mass, the bending of space, is a theory of the smooth, continuous, large-scale structure of space-time. It treats space and time as a flexible fabric that curves and stretches in response to mass and energy. It works magnificently across an enormous range, from the fall of an apple to the orbits of planets, to the bending of light around galaxies, to the behavior of clocks in orbit. But at the center of a collapsed object, and as we will see, at the very beginning of the universe, it points toward conditions so extreme that the fabric description itself seems to fail. Something else must take over, some deeper account of what space and time are made of, and we do not yet have it in complete form. There is a further twist that has troubled physicists deeply and that bears directly on the nature of time and its direction. When something falls into one of these objects and crosses the horizon, it appears, from the outside, to be lost from the universe entirely, its information sealed behind a boundary that nothing can cross outward. For a long time it seemed that whatever fell in was simply gone, removed from the outside universe forever. But this collides with a principle that runs deep in the rest of physics. The principle that information is never truly destroyed, that the details of the present are always, in principle, recoverable from the details of the future and the past. The fundamental laws, as we noted early on, work the same forward and backward, and this reversibility depends on information being preserved. If things that fall past the horizon are genuinely erased, then that preservation fails, and one of the deepest expected symmetries of physics is broken at the edge of these objects. Whether and how information escapes, and what this implies about the structure of time near the horizon, remains one of the most actively debated questions in the field, still without a settled answer. What these extreme objects show us, above all, is that time is not the rigid, universal background we took it to be at the start. It bends, slows, and reshapes itself so thoroughly that observers can disagree about whether an event ever occurs, and it can warp until our best theory of it collapses. But this collapse is not the end of the story. It is a doorway. It tells us that the smooth space-time of the theory of gravity cannot be the final word, that beneath it there must be something deeper, some more fundamental account of time from which the smooth fabric emerges. And there is another realm, utterly different from the crushing gravity of collapsed objects, where the smooth picture of time also fails, where time stops behaving like a flowing quantity and starts behaving like something else entirely. That realm is not the domain of the largest and heaviest objects, but of the smallest. What happens to time when we descend into the world of the very small, where the rules of the quantum govern everything? Descend into the world of the very small, and the smooth, flowing time we have been tracking begins to behave in ways that resist every intuition we have built up. The realm of atoms and the particles within them is governed by quantum mechanics, the most precisely tested theory in all of science, confirmed to extraordinary accuracy across countless experiments. Yet within this theory, time occupies a peculiar and unresolved position. It does not slow or bend here as it does under gravity or high speed. Something more basic is odd. Time in quantum mechanics behaves unlike every other quantity the theory describes, and the difference points to a gap in our understanding that has never been closed. To see the oddity, we first have to understand how quantum mechanics treats the things it describes. In the everyday world, an object has definite properties at every moment. A ball is in a particular place, moving at a particular speed. We may not know these values precisely, but we assume they exist, that the ball really is somewhere, really is moving at some rate, whether or not we measure it. Quantum mechanics overturns this assumption. It says that before measurement, a small object like an electron does not possess a single definite position. Instead, it exists in a blend of many possible positions at once, a spread of potential locations described by a mathematical object that assigns a certain weight to each possibility. This spread is not a reflection of our ignorance. It is, as far as the theory is concerned, the actual state of the electron. The electron is genuinely not in one place until something forces the issue. That forcing is measurement. When we measure the position of the electron, we do not simply reveal where it secretly was. According to the standard account, the act of measurement changes the situation abruptly. The spread of possibilities collapses to a single outcome. Before measurement, many positions, each with its own weight. After measurement, one position, definite and real, and crucially, which outcome occurs, is not determined in advance. The theory gives only the probabilities, the odds of each possible result. It cannot say which result will actually happen on any given try, only how likely each one is. Repeat the measurement many times on identically prepared electrons, and the outcomes distribute themselves according to those probabilities. But each individual outcome arrives without any prior fact that fixed it. This is one of the strangest features of quantum mechanics, and it has resisted every attempt to explain it away for a full century. Now notice how time enters this picture, because this is where the trouble lies. Between measurements, the quantum state evolves smoothly and predictably. The spread of possibilities shifts and changes over time according to a definite equation, and that evolution is completely reversible. Run it backward, and it works just as well as forward, exactly like the other fundamental laws we have discussed. In this smooth evolution, time behaves like a steady background parameter, ticking along evenly, carrying the quantum state from one configuration to the next. There is no arrow here, no built-in direction, nothing that distinguishes past from future. The equation governing the quantum state left to itself is as time-symmetric as everything else at the foundations of physics. But the moment of measurement is different. When the spread collapses to a single outcome, that collapse is not reversible. You cannot run it backward. Once the electron has been found in a definite place, the many possibilities that existed before are gone, and there is no way to reconstruct them from the single result. The measurement introduces a sharp before and after, a clear direction, a moment when many became one and cannot become many again. So quantum mechanics seems to contain two entirely different kinds of time behavior. Between measurements, smooth, reversible, directionless evolution. At measurement, abrupt, irreversible, directional collapse. And the theory in its standard form does not explain how these two fit together or what physically distinguishes a measurement from any other interaction. This is the notorious measurement problem, and at its heart is a puzzle about time and its direction. There is a deeper structural oddity, one that becomes visible when quantum mechanics is set beside the theory of gravity we explored earlier. In the theory of gravity, time is flexible. It bends, slows, and mixes with space, and it is treated on the same footing as the dimensions of space, all woven together into a single flexible fabric. But in quantum mechanics, time plays a completely different role. It is not one of the things the theory describes, not a quantity with a spread of possible values, not something that gets measured with uncertainty. Instead, time is a fixed background, an external parameter that ticks along evenly and against which everything else is described. Position is uncertain, spread across possibilities. Energy is uncertain. Nearly every quantity the theory handles can be blurry, indefinite, spread out. But time is not among them. Time stands outside, sharp and definite, a steady stage on which the quantum drama plays out. This is a strange asymmetry, and it becomes a serious problem when we try to combine quantum mechanics with the theory of gravity. In one theory, time is a flexible participant, bending and stretching along with space. In the other, time is a rigid external backdrop, unbending and precise. These two roles are incompatible. You cannot simply merge a theory in which time bends with a theory in which time is a fixed stage. The very meaning of time differs between them. This clash is one of the central obstacles to building a unified theory of physics, a single framework that would cover both the very large and heavy, where gravity dominates, and the very small, where quantum effects rule. The obstacle is not merely technical, it is conceptual, and it centers precisely on the nature of time. The quantum world offers another window onto the strangeness of time through a phenomenon that entangles the fates of separated particles. Under the right conditions, two particles can be prepared in a joint quantum state such that they are linked, their properties correlated in a way that persists even when they are carried far apart. Measure one, and the outcome is instantly correlated with what you would find if you measured the other, no matter how great the distance between them. This linkage does not fit comfortably into the picture of influences traveling from place to place at or below the speed of light, taking time to cross the intervening space. The correlations appear without any signal passing between the particles, without any lapse of time for such a signal to travel. This does not allow faster-than-light messaging, for reasons woven deep into the theory, but it does reveal a kind of connection between separated events that sits uneasily with our ordinary picture of causes preceding effects in a tidy temporal order. The quantum world contains relationships that do not seem to respect the neat sequencing of before and after that we take for granted. There is also a curious flexibility in how quantum processes can be described in time. In many quantum experiments, whether a particle behaves one way or another can seem to depend on choices made after the particle has already begun its journey, as though the later choice reaches back to shape the earlier behavior. Careful analysis shows that no actual signal travels backward in time, and that causes still cannot be influenced by their effects in any way we could exploit. But the ease with which quantum descriptions can be run in either temporal direction, and the difficulty of pinning down exactly when a quantum event becomes definite, both suggest that the sharp, flowing time of our experience is not built into the quantum foundations. At that level, time seems more like a bookkeeping device for organizing correlations than like a river carrying events from past to future. All of this points toward a conclusion that has been forming throughout our investigation. The flowing, directional, universal time of ordinary experience does not appear at the foundations of physics. In the smooth evolution of the quantum state, there is no arrow. In the fundamental laws, forward and backward are equivalent. In the theory of gravity, there is no universal present, no shared now. And in quantum mechanics, time sits outside the description entirely, a rigid stage rather than a participant, incompatible with the flexible time of gravity. Everywhere we look at the foundations, the rich temporal structure of our experience thins out, until what remains is something far more austere than the time we thought we knew. And yet our experience is emphatic. Time does flow. The present does feel real and singular. The past is fixed and the future open. We remember backward and act forward. The arrow of time is not a subtle effect we have to strain to detect. It is the most pervasive feature of existence, present in every moment of every life. So we face a genuine tension, perhaps the central tension in the whole subject. The physics at the foundations is nearly silent about the features of time we find most undeniable. If the fundamental laws do not distinguish past from future, and if the present has no place in the equations, then where do these overwhelming features of our experience come from? Why does time, which seems so directionless and impersonal in the deep laws, present itself to us as a flowing river with a definite and unmistakable current? The tension is real and it demands an answer. The fundamental laws barely distinguish past from future, Yet our experience is dominated by that distinction. Something must bridge the gap, and the leading answer, worked out over more than a century and still the best we have, does not come from the laws of motion at all. It comes from a different quarter entirely, from the study of heat, order, and disorder, from a quantity called entropy. The arrow of time on this account is not written into the basic rules of physics. It emerges from the way things are arranged, and above all, from the way the universe as a whole began. Start with the observation that cries out for explanation. In the world around us, certain processes happen in one direction and never in reverse. A hot cup of coffee cools to room temperature. It never spontaneously heats up while the room cools. A drop of ink spreads through a glass of water until the color is uniform. It never gathers itself back into a concentrated drop. A structure crumbles, a smell disperses, a stack topples. In every case, we recognize instantly which direction is forward, because the reverse never happens. And yet, as we have seen, the fundamental laws governing each atom in these processes work equally well in both directions. Nothing in the laws forbids the coffee from heating up, the ink from gathering, the ruins from reassembling. So why does the world run so decisively one way? The answer lies in a distinction between two ways of describing a system. Consider the air in a room. At the finest level, the exact state of the air is specified by the precise position and motion of every single molecule, an unimaginably detailed description. But we never perceive the air this way. What we perceive are the broad overall properties, the temperature, the pressure, the density, averaged over vast numbers of molecules. Many different detailed arrangements of molecules produce the same overall properties. If two molecules swap places, or a great many of them shift slightly, the temperature and pressure we measure do not change at all. So each overall condition of the air corresponds to an enormous number of distinct detailed arrangements, all of which look identical to us at the level we can perceive. Entropy is, in essence, a measure of how many detailed arrangements correspond to a given overall condition. A condition that can be produced by a vast number of arrangements has high entropy. A condition that can be produced by only a few arrangements has low entropy. And here is the crucial point. There are overwhelmingly more ways for molecules to be spread out, mixed, and disordered than there are ways for them to be concentrated, separated, and ordered. Order is rare among the possible arrangements. Disorder is common. If you place a drop of ink in water, there are only a relatively small number of arrangements in which the ink molecules stay clustered in a drop, but an astronomically larger number in which they are dispersed throughout the water. As the molecules jostle and move at random, they are simply far more likely to wander into one of the countless dispersed arrangements than into one of the few concentrated ones. So the ink spreads, not because any law forces it to, but because spread-out arrangements vastly outnumber concentrated ones, and random motion tends to land the system in the more numerous kind of arrangement. This is the statistical origin of the arrow of time. Systems evolve from less probable arrangements toward more probable ones, from lower entropy toward higher entropy. Not because the laws prefer this direction, but because higher entropy conditions are so overwhelmingly more numerous that a system stumbling among arrangements is almost certain to end up in one. The coffee cools because there are vastly more arrangements in which its heat is spread evenly through the room than arrangements in which it stays concentrated in the cup. The tendency of entropy to increase is not a law in the same sense as the laws of motion. It is a matter of overwhelming probability, so overwhelming that in practice it never fails for any system of ordinary size. This tendency for entropy to increase over time is often called the second law, and it is the closest thing physics has to a fundamental arrow, a built-in distinction between forward and backward. Forward in time is the direction in which entropy increases, in which order gives way to disorder, in which the improbable settles into the probable. But this raises a deeper question, one that pushes the puzzle back a step rather than resolving it. If systems tend toward disorder because disordered arrangements are more numerous, then why is there any order to begin with? Why is the coffee ever hot, the ink ever concentrated, the structure ever standing? For entropy to increase, it must start low. A system can only move from order to disorder if it began in a state of order. And order, we have just said, is extraordinarily rare among possible arrangements. So the existence of any order at all, anywhere, demands explanation. Why does the universe contain the low entropy conditions that make the increase of entropy, and hence the arrow of time, possible? The answer that physics has arrived at reaches all the way back to the beginning. The universe today is full of order, full of low entropy structures, full of the raw material for entropy to increase, because the universe began in a state of extraordinarily low entropy. In its earliest moments, the universe was arranged in a very special, very ordered, very improbable condition, and everything that has happened since, all the spreading and mixing and cooling and disordering, has been the long unfolding of that initial order into ever greater disorder. The arrow of time we experience, the relentless forward direction of every process around us, traces back to the fact that the universe started in a low entropy state and has been increasing in entropy ever since. The current of time flows forward because it began at a source of exceptional order, and it has been running downhill toward disorder ever since. This is a remarkable idea, and it deserves to be felt in its full strangeness. The reason your coffee cools, the reason you remember the past and not the future, the reason effects follow causes and not the other way around, the reason the world has a direction at all, ultimately traces back to the particular condition of the universe in its earliest moments. The arrow of time is not local. It is not generated freshly in each cup of coffee or each spreading drop of ink. It is inherited, passed down from the low entropy beginning of the cosmos, expressed anew in every process that increases disorder. Every forward-running event in your life is, in a sense, part of the same vast unfolding that began when the universe was young and exceptionally ordered. It also explains features of time that might otherwise seem unconnected. Consider memory. We remember the past but not the future, and this asymmetry is deeply tied to entropy. Forming a memory, recording information about the world, is a physical process that depends on the entropy difference between past and future. A record, a memory, a trace of something that happened, is a form of order imposed by an event, and such records can only be reliably formed in a universe where entropy increases, where there is a clear low entropy past to leave traces of. The direction in which we can hold records, the past, is the direction of lower entropy. The direction in which we cannot, the future, is the direction of higher entropy. The very fact that we experience time as flowing from a remembered past into an unknown future is bound up with the entropy gradient inherited from the beginning. Our sense of moving through time, of the past being settled and the future open, may be, at bottom, a reflection of the fact that we are creatures living in the midst of a long slide from cosmic order toward cosmic disorder. Yet even this leaves something unexplained, and honesty requires us to name it. We have pushed the origin of the arrow of time back to the low entropy beginning of the universe. But why did the universe begin in such an ordered, low entropy state? Among all the ways the early universe might have been arranged, the ordered ones are extraordinarily rare, and the disordered ones overwhelmingly common. If the initial condition had been chosen at random, so to speak, from among all possibilities, it would almost certainly have been high entropy, disordered, and no arrow of time would ever have emerged. But it was not. The universe began in one of the exceedingly rare ordered conditions, and this fact, on which the entire directionality of time depends, is not itself explained by the laws of physics. It is, so far, simply a fact about how things started, a special initial condition whose origin remains open. This is where the arrow of time leads us inexorably to the beginning of the universe. We cannot explain the direction of time without explaining the low entropy start, and we cannot explain the low entropy start without asking what the beginning of the universe actually was. The current of time points back toward its source, and the source lies at the very origin of everything, in the earliest moments of the cosmos, where the low entropy condition was set. To understand time, then, we are forced to ask about its beginning. What was the origin of the universe, and what could it possibly mean for time itself to have had a start? The current of time points back toward its source, and the source lies at the beginning of the universe. But asking about that beginning immediately confronts us with a question that borders on the unthinkable. What does it mean for time itself to have a start? We are comfortable, more or less, with the idea that events have beginnings. A life begins, a storm begins, a sound begins. In every such case, there was a time before the beginning, a stretch of earlier moments during which the thing had not yet started. But the beginning of time cannot be like this. If time itself began, then there was no before, no earlier stretch of moments waiting for time to start, because moments are precisely what time consists of. The beginning of time would be a boundary beyond which the word before loses its meaning. This is one of the hardest ideas in all of physics to hold steadily in the mind, and yet the evidence points toward exactly such a boundary. The evidence begins with a simple, sweeping observation. The universe is expanding. Distant galaxies are moving away from us, and from one another in a systematic way, with more distant galaxies receding faster. This expansion is not a matter of galaxies flying apart through space from some central explosion. It is the expansion of space itself, the stretching of the distances between things, so that every observer, anywhere in the universe, sees the same general pattern of everything receding. Space is growing, carrying the galaxies along with it, and this growth has been measured with great care and confirmed by many independent lines of evidence. The universe today is larger than it was yesterday, and larger than it was 1 billion years ago. Run this expansion backward in imagination, and the consequence is inescapable. If space is growing, then in the past it was smaller. The galaxies were closer together. Go back far enough, and everything that is now spread across the vast reaches of the cosmos was packed into a much smaller volume, hotter and denser than anything that exists today. Continue backward, and the density and temperature climb without limit, the entire observable universe compressed toward a single point of unimaginable concentration. This backward extrapolation points toward a beginning, a moment when the expansion started, when the universe was in a state of extreme density and heat from which all subsequent expansion has proceeded. This is the picture of the beginning that has come to be called the hot early universe, the origin from which the expanding cosmos we see today has unfolded. The evidence for this is not merely the backward projection of the expansion. It is written across the sky in a form we can observe directly. When the universe was very young, hot, and dense, it was filled with a glowing plasma, too hot for atoms to hold together, permeated by intense radiation. As the universe expanded and cooled, a moment came when it became cool enough for atoms to form and for radiation to travel freely. And that ancient radiation has been streaming through space ever since. It fills the entire sky, coming from every direction, stretched by the expansion of the universe into a faint glow of microwaves. This background glow has been detected and mapped in exquisite detail, and it matches the predictions of the hot, early universe with remarkable precision. It is, in effect, an image of the cosmos as it was in its infancy, a direct observation of the ancient, hot, dense state from which everything grew. The beginning is not merely inferred, its afterglow is still arriving, faintly, at every point in space, at every moment. So the universe had a hot, dense, early state, and this is established with great confidence. But the question of the true beginning, the very first moment, the origin of time itself, takes us to the edge of what physics can currently say. As we extrapolate backward toward that first instant, the density and temperature and warping of space-time climb toward the extreme, and we approach exactly the kind of condition we encountered at the center of collapsed objects, where the theory of gravity predicts its own breakdown. Near the very beginning, the smooth fabric of space-time, curving and stretching in response to the matter and energy within it, is pushed toward infinite curvature, toward a condition the equations cannot describe. The theory that so successfully traces the expansion of the universe back through billions of years points, at the very first moment, toward a place where it fails, where the description in terms of smooth space-time collapses, just as it did at the center of the most extreme objects. This failure is significant, and it must be understood correctly. It does not mean the theory is wrong. It means the theory is incomplete, that it has been pushed into a regime where it no longer applies, where some deeper account is needed. The theory of gravity, which gives us the expanding universe and the warping of time near mass, is a theory of smooth, continuous spacetime. But near the very beginning, the conditions are so extreme, the universe so small and dense, that the effects of the quantum world, which we explored earlier, cannot be ignored. At that scale, we would need a theory that combines gravity with quantum mechanics, and as we saw, we do not yet have such a theory in complete form, in large part because the two theories treat time so differently. The very moment we most want to understand, the beginning, is precisely the moment that requires the unified theory we do not possess. This is why the ultimate origin of time remains genuinely open, a frontier rather than a settled fact. We can trace the universe back with confidence through an enormous span of its history, back to when it was a tiny fraction of a second old, hot and dense and expanding. But the very first moment, the boundary where time itself would have begun, lies behind a veil that our current theories cannot lift. To ask what happened at the beginning, or whether there even was a first moment in the strict sense, or what preceded it if the question means anything at all, is to ask questions that reach past the edge of established physics into the territory of careful speculation. That speculation, however, is not idle. It is disciplined by everything we know, and it has produced several serious possibilities worth considering. One possibility is that time did have an absolute beginning, a genuine first moment before which there was quite literally nothing. Not empty space, not a prior universe, not even a before. On this view, the beginning of the universe was the beginning of time itself, and asking what came before is like asking what lies north of the northernmost point. The question has grammatical form but no meaning, because there is no such place, no such moment. Time began, and that beginning was a true boundary, an edge to reality beyond which the concept of earlier simply does not apply. Another possibility is that what we call the beginning was not truly the beginning of everything, but a transition. a moment when our universe emerged from some prior state or larger structure. On this view, the hot, dense early universe was not the first thing, but a phase, arising from something that came before, whether an earlier contracting universe that collapsed and rebounded, or a vast encompassing structure within which universes form, or some other arrangement in which our beginning was a local event rather than an absolute one. These ideas differ enormously in their details, but they share the feature that time, or something like it, extends back beyond what we can see, so that our beginning is a chapter rather than the first page. In these pictures, the question of the ultimate origin is pushed further back, perhaps indefinitely, and whether it ever reaches a true first moment remains unknown. There is also a subtler possibility, one that dissolves the question rather than answering it. It may be that at the very beginning, under the extreme conditions where quantum effects and gravity combine, time does not behave like a line with a definite starting point at all. It may be that the sharp distinction between time and space softens near the beginning, so that what we think of as the first moment is not a sharp edge but a smooth, rounded region, without a definite boundary, in the way that the surface of a sphere has no edge and no starting point, even though it is finite. On this view, asking what happened before the beginning would be like asking what lies south of the southernmost point. There is no such place, not because you hit a wall, but because the geometry simply closes off smoothly, with nothing beyond. Time would be finite in the past, but without a sharp first instant, curving into something else rather than starting abruptly. This idea remains speculative, tied to our incomplete understanding of how gravity and the quantum world combine, but it illustrates how strange the true beginning might be, and how our ordinary notions of starting and before may simply fail to apply. What all these possibilities share is the recognition that time near the beginning is not the familiar time of everyday life, and perhaps not even the bent and flexible time of the theory of gravity, but something stranger, tied to physics we have not yet worked out. And this returns us from the largest question of all, the origin of the universe, to the deepest question about the nature of time. For in trying to understand the beginning, we keep running into the same obstacle, the same missing piece. To describe the first moment, we need to combine the theory in which time bends with the theory in which time stands rigidly apart. And when physicists have tried to do exactly that, to write down the fundamental equation for a universe that is both quantum and gravitational, they have encountered something that overturns everything we have assumed. In that equation, at the very foundation, time does not appear at all. When physicists set out to write the fundamental equation for a universe that is both quantum and gravitational, they expected difficulty. What they did not expect was that time would vanish from the equation entirely. This is not a figure of speech or a loose way of describing some subtle effect. In the most direct attempt to combine the theory of gravity with quantum mechanics, applied to the universe as a whole, the resulting equation contains no time variable, the quantity that in every other equation of physics marks the passage of time, that ticks along and carries the system from one state to the next, is simply absent. The equation describes a universe that does not evolve in time, because there is no time in it for the universe to evolve through. This result has a name, and it is often called the problem of time, and it may be the single strangest thing modern physics has uncovered about the subject. To understand how time could drop out of the deepest equation, we have to recall the two ways time appears in the theories we are trying to combine. In quantum mechanics, time is an external background, a fixed parameter ticking along outside the system, against which the quantum state changes. The central equation of quantum mechanics describes how the state evolves as this external time advances. In the theory of gravity, by contrast, time is not external. It is part of the flexible space-time fabric, bending and stretching along with space, with no fixed background clock standing outside. Now try to apply quantum mechanics to gravity itself, to the whole of space-time. The external clock that quantum mechanics relies on is gone, because in gravity, there is no external clock. Time was supposed to be part of the very fabric we are now trying to describe quantum mechanically. So there is nothing left outside to play the role of the ticking background parameter. And when the equation is written down under these conditions, the time variable that quantum mechanics normally depends on has nowhere to come from. It disappears. What remains is an equation that describes all the possible configurations of the universe, all the possible ways the contents of the cosmos can be arranged, but with no variable specifying when. It is as though the equation contains the entire universe, every possible arrangement of everything, laid out not in a sequence, but all together, without any marker of before and after, without any flow from one arrangement to the next. The equation is, in a sense, timeless. It describes a frozen totality, a complete catalog of possible states of the universe, related to one another by the structure of the equation, but not ordered into a temporal progression. Nothing in it says that one configuration comes first and another follows. The stage on which we have watched the entire drama of time unfold, the steady background against which everything happens, is not present in the deepest equation we have been able to write. This is a staggering result, and it forces a question that sounds almost absurd. If the fundamental equation of the universe contains no time, then why do we experience time so vividly? Why does anything ever seem to happen if the deepest description is frozen and changeless? How can a timeless equation give rise to a world so thoroughly saturated with time, with flow, with change, with the relentless passage from past to future? Either the equation is wrong or incomplete, or time as we experience it is not fundamental, but something that arises out of a deeper reality that does not itself contain time. And the more physicists have examined the situation, the more seriously they have taken the second possibility. The leading way of making sense of a timeless fundamental equation is to reconsider what we mean by time in the first place. We have been assuming throughout that time is a thing in itself, an independent quantity that flows whether or not anything happens. But there is an older, deeper idea, one that stretches back centuries in the debate over the nature of time. That time is not an independent thing at all, but merely a way of describing change, a summary of how the parts of the universe alter in relation to one another. On this view, there is no time apart from the changing configurations of things. Time is not the container in which change happens. It is the accounting we keep of change itself. And if time is nothing but the relation of changing things, then a fundamental equation might well contain no separate time variable, because there is no separate time to include. The equation would contain only the configurations and their relations, and time would be something we read off from those relations, not something written into the equation as an independent ingredient. Here is how this dissolves the paradox of a timeless equation giving rise to a temporal world. Imagine the fundamental description not as a sequence of moments, but as a vast collection of possible configurations of the universe, each one a complete snapshot of everything, every particle in every position, every field in every state. Among these configurations, some contain what look like records of others. A configuration might contain a structure, a brain, a photograph, a geological layer that carries an imprint corresponding to another configuration, as though the second were a memory or trace of the first. Configurations that contain records of other configurations are related in a way that lets us order them, that lets us say this one is later, because it contains traces of that earlier one. Time on this picture is the ordering we impose by following the chains of records, the sequences of configurations in which each contains traces of those we call earlier. The flow of time would be our movement along these chains, not a movement of the configurations themselves, which simply exist all together in the timeless totality described by the equation. This is a subtle and difficult idea, and it is worth dwelling on, because it turns our ordinary picture inside out. Normally, we think of the present moment as real and the past and future as, respectively, gone and not yet arrived. But on this view, there is no single present moving through time. There is instead a vast collection of configurations, each complete in itself, each containing its own records of others, and the sense of being in a particular now, with a definite past behind and future ahead, is a feature of each configuration, arising from the records it contains. Each configuration that contains a thinking being would contain, within that being, a sense of the present, a set of memories of the past, an anticipation of the future, all encoded in the arrangement of matter at that configuration. The experience of being at a particular moment, of time flowing, would be present in each configuration, not because time is flowing through them, but because each configuration contains the structures that generate that experience. The flow of time would be, in a strict sense, an aspect of the configurations themselves, rather than something happening to them. If this is right, then the deepest reality is timeless, and time is emergent, a feature that arises from the relations among timeless configurations, rather than a fundamental ingredient of the universe. This would explain why time is absent from the fundamental equation. It is absent because it was never fundamental. It emerges at a higher level of description from the ordering of configurations by their records, in much the way that temperature emerges from the motion of molecules without being a property of any individual molecule. A single molecule has no temperature. Temperature is a feature that appears only when we consider vast numbers of molecules together and describe their collective behavior. Perhaps time is similar, absent at the deepest level, appearing only when we consider the relations among many configurations and describe the patterns of records and correlations they contain. It must be said clearly that this is not established fact. The problem of time is a real feature of the attempt to combine gravity and the quantum world. But the interpretation of that timelessness, the idea that time emerges from a deeper timeless reality, remains a hypothesis, one serious proposal among several, still debated, still incomplete. The fundamental equation itself is not fully understood, and there is no agreement on how to extract from it the ordinary flowing time of experience, or even whether the equation in its current form is correct. What can be said is that the disappearance of time from the deepest equation is a genuine result, not an artifact, and that it points, however uncertainly, toward the possibility that time is not fundamental. This possibility, once merely a philosophical speculation, has become something that our most serious attempts at fundamental physics seem to suggest. Notice how much of our investigation this would tie together. We found that the flow of time does not appear in the fundamental laws, which are indifferent to direction. We found that the present moment has no place in the equations, no marker singling out now. We found that the universal present dissolves under the relativity of simultaneity, that different observers slice time differently with no privileged slicing. We found that the arrow of time comes not from the laws, but from the low entropy beginning, an inherited condition rather than a fundamental feature. And now we find that in the deepest equation, time itself is absent. Each of these results, discovered separately, points in the same direction. They all suggest that the rich, flowing, directional, universal time of our experience is not written into the foundations of reality, but is something that appears at higher levels, emerging from a deeper structure that does not itself contain it. If that is so, then the final question is not whether time emerges, but how. How does a timeless foundation give rise to the vivid temporal world we inhabit? How do the relations among timeless configurations produce the flow we feel, the direction we cannot reverse, the present that seems so undeniably real? This is where the investigation reaches its furthest edge, where established physics gives way to the boldest ideas physicists are willing to entertain. If time is not fundamental, then it is something the universe produces, and to understand time fully, we would have to understand how something so central to our existence could arise from a reality that, at its deepest level, does without it entirely. If time is not fundamental, then it is something the universe produces, and the task becomes understanding how. This is the furthest edge of the investigation, where established results give way to the most ambitious ideas in physics, ideas still being worked out, still contested, still incomplete. But they are not arbitrary. They grow directly out of everything we have found, and they represent the serious attempts of physicists to answer the question that all our previous discoveries have forced upon us. If the deepest reality is timeless, how does time emerge from it? How does a changeless foundation give rise to the flowing, directional, vivid time of our experience? Begin by taking seriously what emergence means, because it is the key idea and it is one physics has used successfully many times before. Something is emergent when it appears at one level of description, but not at a deeper one, arising from the collective behavior of underlying parts that do not individually possess it. We have already met one example. Temperature is emergent. A single molecule has no temperature. Temperature exists only for large collections of molecules as a description of their average motion. It is perfectly real, something we measure and feel and depend on. Yet it is not a fundamental property written into the basic laws. It emerges from the behavior of many parts. The proposal at the frontier of the physics of time is that time is emergent in a similar way, real at the level of our experience, but arising from a deeper level that does not contain it, in the way temperature arises from molecules that individually have none. The most developed versions of this idea connect the emergence of time to the strange quantum linkage we encountered earlier, the phenomenon by which separated parts of a quantum system can be bound together, their properties correlated in ways that persist across distance. This linkage, which seemed at first like a curiosity, has come to be seen by many physicists as something far more central, possibly the very thread from which space and time are woven. The suggestion is that at the deepest level, there are no space and time at all, only a vast web of quantum relationships, a network of correlations among the fundamental parts of reality. Space, on this view, arises from the pattern of these correlations, with things that are strongly linked appearing close together and things weakly linked appearing far apart. Distance itself would be a measure of how strongly parts of the underlying web are quantum linked, and time likewise would arise from the structure of this web, from the way the correlations are organized, rather than existing as an independent stage on which the web is arranged. To feel how this might work, consider again the idea of records and correlations that we met in discussing the timeless equation. Suppose the fundamental reality is a web of quantum relationships with no time built in. Within this web, certain patterns of correlation have the character of records, structures that carry information about other parts of the web as a memory carries information about the past. Where such records exist, they impose an ordering. A part of the web that contains records of many other parts, but of which those other parts contain no record in return, sits naturally at the later end of an ordering, just as a photograph comes after the scene it depicts, never before. Following these chains of records through the web produces a direction, a sequence, an ordering that we would recognize as the flow of time. Time would be, in this picture, the reading off of order from the structure of correlations in a fundamentally timeless quantum web. The flow we experience would be our passage along the chains of records, and the direction of that flow, the arrow, would come from the imbalance in how records are distributed through the web. This connects, remarkably, back to entropy and the low entropy beginning. For records to exist, for the chains that give time its direction to form, the underlying web must have a particular structure, one with the right kind of imbalance, the right gradient, to support the formation of records in a consistent direction. This is, at bottom, the same requirement we met when we traced the arrow of time to the low entropy beginning of the universe. The direction of time, the existence of records, the increase of entropy, and the special condition of the early universe all appear to be aspects of a single underlying fact about the structure of reality. Whether we describe it as a low entropy initial state or as a particular pattern in the fundamental web of correlations, the various arrows of time we have encountered, the thermodynamic arrow of increasing disorder, the psychological arrow of memory and anticipation, the cosmological arrow of the expanding universe, would all be expressions of this one deep feature, all pointing the same way because they all derive from the same source. There is a further and even more ambitious element to some of these ideas, connecting the emergence of time to gravity itself. Recall that gravity, in the theory that describes it best, is the warping of space-time, the bending of the very fabric of space and time in response to mass and energy. If space and time themselves emerge from a deeper quantum web, then gravity, which is the flexing of space-time, must also emerge from that web. And indeed, some of the most striking recent work in physics suggests exactly this, that the equations describing the warping of space-time, the equations of gravity, can be derived from the properties of quantum correlations in the underlying web. In these approaches, gravity is not a fundamental force, but a consequence of how quantum information is organized, and space-time, with its curvature and its time, is a large-scale expression of the deeper web of relationships. This would unite in a single picture the two great theories that we found so difficult to reconcile, the quantum world and the theory of gravity, by showing that space-time and gravity emerge from the quantum web, rather than standing as separate fundamental things that must somehow be forced together. If all of this is right, and it remains a large if, then the picture of time that emerges is profoundly different from the one we began with. Time would not be a river carrying us forward. It would not be a fundamental dimension, a fixed stage, or an independent flowing quantity. It would be a feature that arises from the organization of a timeless quantum web, a pattern read off from the structure of correlations, meaningful and real at the level of our experience, but absent from the deepest description of reality. The flow we feel, the direction we cannot reverse, the present that seems so vivid, would all be aspects of how conscious beings, themselves patterns within the web, experience their place in the ordering of records and correlations. Time would be, in the fullest sense, emergent, produced by the universe rather than presupposed by it. We must be careful and honest here, because this is the region of the investigation where speculation is greatest and confirmation is least. The idea that time emerges from a timeless quantum web is not established physics. It is a family of proposals, some more developed than others, tied together by the shared conviction that time is not fundamental and by the suggestive results that point in that direction. There is not yet a complete, confirmed theory that combines gravity and the quantum world, and without such a theory, the emergence of time remains a hypothesis rather than a fact. The equations that suggest time might be absent at the deepest level are not fully understood, and the path from a timeless foundation to the flowing time of experience has not been fully traced. What we have are strong hints, converging clues, and serious frameworks under active development, not a finished answer. The physics of time at its frontier is a work in progress, and the boldest ideas may yet be revised or replaced. But even acknowledging all this uncertainty, something remarkable has happened over the course of this investigation, and it is worth naming clearly. We began with time as the most obvious and unquestioned thing in the world, the steady universal flow that carries us from past to future. And step by step, guided not by speculation, but by measurement and evidence, we have watched that picture come apart. We found that the universal present does not exist, that simultaneity depends on motion. We found that time slows with speed and with gravity, that no two clocks need agree, that there is no master clock for the cosmos. We found that the direction of time, its forward flow, is not in the fundamental laws, but inherited from the low entropy beginning of the universe. We found that in the quantum world, time behaves unlike anything else, standing outside the description as a rigid background. And we found that in the deepest equation we have been able to write, time disappears entirely, suggesting that it may not be fundamental at all, but something that emerges from a deeper, timeless reality. Each of these discoveries was forced upon us by evidence, by the stubborn results of careful measurement, by clocks flown on aircraft and carried up towers, by particles raining through the atmosphere, by the afterglow of the early universe, by the relentless internal logic of theories tested to extraordinary precision. This is not idle philosophy. It is where the physics leads, and where it leads is to a view of time utterly unlike the one we started with. A view in which the most familiar feature of existence may be, at bottom, a kind of illusion, or more precisely, an appearance. Something real at our level but absent from the foundations, produced by the universe rather than built into it. What remains at the end is not a tidy answer, but a transformed question. We can no longer ask simply what time is, as though it were one clear thing waiting to be defined. We have to ask instead how time emerges, from what, and why it takes the form it does, why it flows, why it points forward, why the present feels so real when the equations know nothing of it. These questions are open, and they sit at the growing edge of physics, where the next great theory, the one that finally unites gravity and the quantum world, may someday provide answers we cannot yet imagine. Until then, we live inside time, carried by its flow, certain of its passage, while the deepest science we possess quietly suggests that this most intimate and inescapable feature of our lives may not be a fundamental part of the universe at all, but something the universe, in ways we are only beginning to grasp, brings into being. And perhaps the most honest thing we can say is that time, which we thought we understood better than anything, turns out to be the deepest unsolved mystery we have ever tried to measure.